Okay, so this lesson is going to be on real quick on hybridization of atomic orbitals. And then we're going to also talk about how we can use some rules to predict what the shape of molecules are from these types of atomic orbitals. And basically you understand that, or you may or may not understand that an sp orbital, any type, an sp3, sp2, and sp, is a combination of the valence s orbital and the valence p orbitals in an atom. So when an atom goes into bond with another atom, it's going to use all of its valence electrons that it needs to make a bond. And don't forget, even though the s electrons are a little bit lower in energy than the p electrons in the valence shell, by forming a hybrid orbital, we lower the energy state and we allow a more energy favorable bond situation. So that's what we're going to look at real quick here on this video. Okay, so let's look at the simplest one, or the one that's easiest to describe first, and that is the sp3 orbital. And don't forget, the sp3 orbital is basically a combination of the valence s orbital and all three valence p orbitals, right? We have even though we have the p orbital, it's as a loose term, there are three orbits, I guess, of the p orbital. There's the px, py, and pz, and they're all orthogonal to each other. So there's they're all basically these dumbbell shapes here, and they're all in plane with each one of the three axes, the 3D axis. So there's a z, there's the x, and then there's a y. And when the s comes in and combines with all three of these to form a new orbital shape, the resultant is four equivalent lobes with that are oriented in a tetrahedral configuration. So that's why molecules like CH4, CCl4 have this tetrahedral orientation, as opposed to this up-down one where you would see from here. All right, because we now have a hybrid orbital as opposed to a single orbital of in three different spaces. All right, let's look at the next orbital series. It's the sp2, and the sp2 only means that it's the valence s orbital is going to combine with two of the p orbitals, and the other p orbital is going to be left unchanged, right? And so these two p orbitals and the s orbital combined, and where they used to be, they're all in the same plane now, and now they have a trigonal shape and arrangement. All right, so the s combined with this one, and then the resultant is three new orbitals. And then when you put them together, it looks like this one over here. We still have a orbital left over in the p that we can use to accept electrons for pi bonding. All right, this is just another look at how this happens, and it shows you the extra empty the atomic orbitals left over for pi bonding. So we have our s from our valence going to combine with two out of the three p orbitals, and we're going to get these new hybrid orbitals here, which combine to make this trigonal planar arrangement. But we still have a we still have a p orbital that's going to be orthogonal to the plane of the trigonal orbital, or the hybrid orbital shape here. So that would be coming out here and going this way, and the other one's going that way. So think of it as a three-pronged propeller with two lobes coming out of the top and bottom of the propeller. And lastly, the last orbital that forms is the sp orbital, and now we only have the valence shell s electrons forming with one of the p orbitals, and we leave the other two p orbitals alone, and they are also now available for pi bonding to accept electrons for pi bonding. And so what you do now is when you make these two orbitals, you have an sp orbital here that can be used to bond to two other things on this end of the orbital and this end of the orbital. Hence the word sp, right? There's two places to bond, and there's two orbitals used to make this new two orbital bond, hybrid orbital. Okay, so now that you know that hopefully have a better understanding of how what we mean by a hybridized orbital for the S and P orbitals, we now kind of use our VESPER knowledge to try to make predictions based on the Lewis structures. And when we do that, we're going to be able to, for the most part, make some pretty accurate shape descriptions of the bond structure around a atom. And this will help us understand how the atom is bonding to its neighboring atoms. So let's look at a couple of examples of this real quick here. And in order to be able to use this chart properly, you're going to be able to be proficient in drawing a Lewis structure for your particular atom. All right. So if you don't know how to do that, you should practice on how to do that. So we're going to look at the first molecule. We're going to look at CH4. So I've drawn the Lewis structure for methane on the top of the paper here. And so let's look at this little chart here and use some of these rules to help us understand what we think the geometry of this will be. Now right now it looks like it's just a four-way cross on a 2D four-way cross, but in reality we know it's probably not that. But let's see how this chart helps us figure out what's going on here. So we're only going to be concerned with what's the bond structure, or what's the shape of the bond structure around the carbon atom there. So our first thing to do is ask the question, how many things are attached to the atom? And so we're only looking at the carbon right now, so we want to know how many things. So we know that hydrogen's attached because we have a bond here, and here's another one. So then there's actually 4 things that are attached to the carbon. And so that's what we got here. And so that's question 1 has been answered. So we have 4. And now we're going to ask the next question here is how many electrons are in lone pairs. So basically we're asking here is how many lone pairs of electrons are there. And so we can go around and count, and we see there's none. There are no lone pairs anywhere. So we looked around and it said nothing. So there's going to be 0. So we're going to follow the path that says 0 here, and then we see that it's calling for an sp3 hybridized tetrahedral with a 109 degree bond angle, and that makes sense. We can show you that structure in a second here. Hold on. So there's our tetrahedral for methane. And you can see here that they do to predict that the bond angle is going to be 109 degrees, which is going to be equal for all the bond angles for all the hydrogen, carbon, hydrogen. So there's the angle that they're looking at here is 109 degrees. And then it'll be the same for this one. It'll be the same for this one. And then you can't see it, but it'll be the same for this one here, this bond angle here. So everything checks out so far. And so our rules make up, what I guess they call them rules, will demonstrate that this is a 109 bond angle, and it's been measured that is the correct bond angle for that. Okay, so I drew a new molecule up here to try and look at this the series of steps that we use to take to help us make predictions on what the hybridization of the atom is. That's we're interested in forming or looking at how it's forming bonds. So in this particular case, I've selected the molecule of water, and I've drawn a Lewis structure of it. Now, this is not the accepted Lewis structure. Remember, the accepted Lewis structure has the water molecule bent, but we're going to use the linear one here because we don't know what the bend angle is yet, and I'm going to make a prediction based on what I see on the chart here. So we're going to look at the central atom, or the atom that we're interested in finding out the bonding space around it and what the shape of that space is. And so our oxygen atoms, we're supposed to count the number of things attached to it. And in this time, we need to make sure that we count the pairs of electrons. They count as one thing. One pair counts as one thing, and because they are attached to the oxygen. So let's look at them real quick here. So we have one here and one here, so that's two so far. The hydrogen we definitely know is attached to the oxygen because we have a bond there, and then the other hydrogen too because we have another bond there. So there's 1, 2, 3, 4. There are 4 things that are directly attached to the oxygen. Even though that there's nothing bonded to the oxygen, the fact that it has unbonded pairs of electrons is going to affect the shape of the molecule. So let's go over to our chart real quick and see what this says here. It says how many things are attached to the atom, and we already knew that's 4, so we're going to go over here to 4. And now we ask the question, how many are lone pairs of electrons? And the answer to that is, well, there's 2, so we're going to go over to 2. And it says we have an sp3 hybridized molecule, but it's bent. And what that means is these 2 electrons here are going to, since there's 4 things around the oxygen, it is a tetrahedral type of structure, but the unbalanced electrons on the oxygen are going to distort that tetrahedral a little bit. So it's not an equivalent tetrahedral, it's going to be distorted, and the bond angle is going to be close to 105 degrees. And the bond angle, what we mean is the bond angle between H, O, and H. So let's look how we would draw that now. Okay, so I've drawn a Lewis structure of oxygen, and you can see here, this is more of the generally accepted drawing for a Lewis structure of oxygen. And we're looking at, this angle here is going to be the one that's 104.9. And if you draw a tetrahedral of this, you're going to have these lone pair kind of sticking out of the plane of the viewing screen, and these lone pairs are going to be pushed back behind the viewing screen because we want to get the maximum angle in between these two. And don't forget, this is a 2D drawing of a 3D molecule. So it does predict it so far, so good as far as predicting and from the hybridization. Okay, I've drawn 3 more structures that we're going to look at real quick, and then I'm going to show you a thing about a little bit of a uniqueness about this chart. So let's do the 3 of them real quick, and I've chosen these for different reasons. So the first one we're going to choose is CO2. And let's look what that was real quick. So we're only looking around the carbon for this particular instance. All right, and so we have how many things attached to the carbon? Well, we only have 1 and 2, right? We don't count the double bond as 3, 4 because it's only one thing attached at the end of that double bond, right? So we just count it once. So we have 1 and then 2. We don't count the lone pair of electrons on the oxygens because they're not directly attached to the carbon. So we have 2 things attached to the carbon. And then, so let's count, while we're still here, let's count how many lone pair. We don't have any lone pair. Even though these are 2 pair here, one of these pairs they're still bonding, right? So they're not lone pair, right? They're bonding pairs of electrons. So now we're going to go to our chart here, and we can say we have 2 things, so we're going to go down to this part of the chart here, and then how many of them are lone pair? 0, and we have an sp hybridized bond here, which makes sense, right? Because the second bond here is no longer a sigma bond, it's a pi bond, and our example is CO2, which is what this is. And it's a linear with the angle of 180 degrees. Remember, we need 3 points to make our angle. 1, 2, 3. Here's our center point. And it's telling me that this is a straight or a flat molecule. The next one we're going to look at real quick is nitrogen. And since there's no central atom here, so we're just going to pick one of the nitrogens. So let's just pick this one. And again, we're going to apply the same rules. how many things are attached to the nitrogen. Even though this is a triple bond, we only count this once, and we don't count the lone pair here as something attached to this nitrogen here, this one. But we do count this lone pair here. So we have two things attached, and so we have two things attached, and then there's one lone pair around the nitrogen that we're looking at here. Because remember we said we're looking at this. It doesn't matter because they're the same, but we're looking at this one. So there's one lone pair, and there's two things attached. So we're going to go down to our 2, and we're looking at our 1, and it says it's an sp hybridized, which makes sense. It's linear, but it doesn't have a bond angle, which also makes sense because you need like I said, you need a point in the middle to make an angle, right? An angle is that, right? So you need a point here to make an angle. Otherwise, it's just a line segment, right? And so there's no angle there, but it is linear. So it's a linear molecule with no bond angle, right? And the last thing we're going to do is let's look at one more real quick. Let's look at the molecule here, formaldehyde. And let's look at that one real quick. So we're going to look at the carbon right here, carbon. And now we have how many things bonded to it? Well, there's 1, there's 2, and then there's 3. Even though that there's a double bond again for the oxygen, and we count it once. So 1, 2, 3. So now we're going to look at what's our hybridization is going to be 3. And then how many of them are lone pair? Well, there's none. So there's 1, 2, 3. So there's 0 lone pair, and it says it's sp2 hybridized, and it's a trigonal planar, and that's exactly what this molecule is. It's just a triangle if you draw it out correctly. Let me just quickly draw the carbon atoms here in the center, and these are at 120 degrees away from each other. So it would look like that with all the electron dots around the oxygen. So that makes it sense. It predicts it's trigonal planar, and it is. And now the last thing I'm going to look at, so as far as these molecules here, that's fine. The last thing we're going to look at is we're going to look at one of the hydrogens around. We'll look at 2 more things real quick. We're going to look at the hydrogen around the carbon here, and we're just going to look at this hydrogen here. So again, we're looking at the bond geometry around the hydrogen. So the question is, how many things are attached to the atom? Well, there's only one thing here, that's the carbon. So we go down to here, and then it says here, hydrogen is the only example. So there you go, hydrogen's the only example. And then let's look at just one more real quick. I know I said I was going to stop there, but let's look at one more real quick. Let's look at the same molecule here. Except we're going to put a chlorine where the hydrogen is, right? So we're going to put a Cl. Let's just do Cl, Cl, and then we're going to have double oxygen, or double bond oxygen, and we'll put it here. I'm running out of room, right? And then let's put some electrons around this one, because we do have those electrons. And now we're going to look at the bond structure, or the orbital shape structure around the chlorine, right? Because we're interested in finding out, because this looks a lot different than the hydrogen. We know there's only one thing bonded to it as far as a bond, but now these lone pairs might come into play as far as the shape. So we're going to look at that real quick. So our rule says, well, how many things are bonded to the chlorine? Well, there's 1, or excuse me, how many things are attached to the chlorine? There's 1, 2, 3, 4. So we have 4 things. And then how many of them are bonding lone pair? And that's 3. And it says here, it is sp3 hybridized, but it's a linear bond, and there's no bond angle. And that's exactly what you're seeing here. It's a linear bond with no bond angle. So this really much makes a lot of sense if you apply the rules and understand what hybridization is, and I hope this was helpful.